Welcome to the second part of this series. In this episode, we will continue to talk to Jim Weninger and examine if we can consider the subatomic world to be also described by bubble dynamics and bubble behaviors.
What can we learn from one scale that'll help answer open questions on the other scale, and just look for even more correlations? To me, that's the short term. And then also jump down in scale yet again, because you're going to find that there's a few features of, like on the nuclear scale, that you're going to need to keep those double layers in mind again. And I mean, a lot of people don't want to go there, but
so I think you explain that, because I know where you're going with that.
Well, yeah, like like gravitational and electrostatic forces are nice inverse square forces. But the one place that electric forces aren't like that is at the sun's surface. If there's double layers, we have an electric field only between the double layers. It's a finite range force, and it only exists there. On the nuclear scale, we're positing, finite range forces, but where no one wants to go is thinking that there could be double layers at that scale, because we think we're so far removed from thinking that there might be charge units so much smaller that they could form double layers. But if we talk about what we see on large scale, and what we accept is that large scale charged objects will surround themselves with a double layer. We just think that charged units in the nucleus, aren't going to do, or the nucleus compared to its environment, it's not going to have double layer. Why? Because there's no units of charge that small that they could form shell around that. But that's the key to getting finite range forces, is finite, you basically are having an electric force, but at in that super small range region then.
Right, because it's got to be very close to the double layer in order to feel, a small distance away from it, and you're shielded. That's the point of the double layer.
And that came up. That idea, though, of smaller units of charge came up when you realize that a laser light beam shows so much of the same patterns and behavior as we see for like a Bessel function filament, including these shells, which they call lobes in a laser beam, but it's still these shells. And it has a lot of the same, self. We know that a laser beam remains coherent for a long period of time, like a Birkeland current in space might have the same diameter without dispersing. And even restoring after there's a disturbance, a laser beam is self-repairing, and so is a Birkeland current. But the key observation is, in a Birkeland current in space, we know what it's made up of. It's made up of, each of the shells even have to be multiple small-scale charged units. If you're going to say that a laser beam is the same thing, it's not going to work. With a laser beam, clearly isn't a bunch of ions and electrons forming into shells. Again, you're going to need to accept that our charged units are way smaller than the same scale we'll need to do to explain double layers around a nucleus. The universe is going to have to be scalable a lot farther down than we're willing to go. Every time we see a larger scale structure in space, people aren't even surprised anymore. When we see walls of galaxies, clusters of galaxies, and on and on.
Yeah, upward is fine, downward is not.
Right. But the more we add to the upper scales, the more that puts us, if we want to say that we're that close to the minimum unit, the closer that, the more that puts us in a special place. If you want to make it go infinite upward, then really we live in this special place in the universe where units don't go down farther in scale. We just happen to be where we're right now, just happen to be seeing the smallest scale.
Yeah, I guess this is that people, you can look up and see an infinitely increasing scale, but looking down, why is that? Why is it that we're uncomfortable thinking that the same wouldn't apply? I don't know. I mean, I guess there's also this whole concept of you could argue whether or not it's true, but the Planck length, and whether you can get anything that's smaller than that, whether that's physically impossible. But who knows? Because that's really, we can't measure to that, so that's sort of an irrelevant discussion. And we see, Lena, let's be clear, we see lots of these, particularly when we're talking about, Bessel functions and, the shapes that plasmas create. We see that repeating at many different scales, from, weather patterns to you know, solar systems to galaxies, and as you say, you know, to the even larger structures. So why would that not happen downwards is an interesting question. And again, it comes back to this idea that we because this is really looking outside of the box, and we're not saying that this is the way forward, that this is it, but we're just thinking that this is a direction that adds to what we already have. It's not replacing it, it's just an additional layer and an additional way of comparing what we can see in terms of bubbles to what we potentially see in terms of plasmas and stars and smaller. I mean, it's an interesting idea that you know, what is a proton? Why should it be a solid surface? You know, maybe it isn't. Maybe it is indeed a spherical thing that is segregated from the surrounding via some sort of double layer. And in which case you would have the same principles. So what happens when one of those double layers collapses? That's an interesting thought.
Mm-hmm.
I mean, I guess that's for me where if you were to compare it, do we see that? I don't think we do we? You can't destroy a proton, or is it that the proton is so much more stable, therefore we just don't see that happening? Or is it to do with timescales, stability on timescales?
Yes, that's one of the timescale ideas. The one that really made me look at in a new light at like what's happening at comparing the solar system scale to the atomic scale. It's one thing to say that transitions are instantaneous, like we get electrons are in one shell or the other, but like if there were these planetary events in the past where a planet suddenly changed its orbit and then stabilized, that's when you compress time to where you could actually see this whole thing happening. That's an effectively instantaneous change. That's quite a difference though from an instantaneous change. But the one thing we're willing to do on the solar system scale is we already accept that, a planet isn't a fundamental unit of matter. If someone said a planet just exploded, for example, you might entertain that idea. That's not hard to imagine, for example, that there was a planet once where as Tom Van Flandern argued, there was a planet out in that shell and then there's not one. But it wasn't that planet suddenly disappeared from there and reappeared somewhere else or any of that. The matter is there. It's just that planet wasn't a fundamental unit and all that matter is redistributed and it could collect again in another shell, but that doesn't mean that the matter, it definitely didn't disappear instantaneously. But we're just not willing to go there with, if you think that we're at the smallest units of matter when we talk about like electron orbitals in the nucleus, then you're not going to get any of those dynamics. But again, like I pointed out, doing the scaling, right? If you want to compare the solar system to an atom, it's not like the planets are electrons. You'd have to say that the heliosphere is like an electron around the sun. And then that gives you a whole different dynamic of what can happen with all that. And also, that's where we see more of an analogy of shapes, too. These shells around stars that can go to, lobes, to open hourglass shapes, to just nice spherical shapes like we think the solar system might have, but we're not sure. It might be spherical, it might not be. It's planetary nebula, in other words, that match the shapes of electron orbitals. It's not planetary orbits for sure. Planetary orbits don't do anything like.
Yeah, this is probably a better one because again, these are all just averaged. They draw them as these very solid lines, but they're not that solid. It's where we estimate them to be. But yes, indeed, here like this, planetary nebula. Anyone, or the equatorial rings around certain things. I mean, some of these shapes, I'm not sure. Well, I don't. Never say never. I'm not sure like this that we would see that in terms of a star, but we might see that in terms of clusters of stars or clusters of galaxies, maybe.
Yeah, I think they're probably better images of orbitals too. And then again, we have to remember the external electric and magnetic fields that aren't shown in the.
Yes, but again, some of these might also, because that the Pulsar one that I sent you where it had the beam coming out on one side. That was the electron beam. And then at 90 degrees to it, it had a smaller, and interestingly enough, it was a fatter, much thicker beam. And that's the one that had that helical structure inside of it. And again, that was like, how do you explain something that's at 90 degrees to the, I presume, if we're going for the beam being the axis of rotation, or where the effectively where the Birkeland current would come in, and that the one at 90 degrees would be the equatorial. Why would the equatorial push out only in one lobe? Normally you'd say, well, that wouldn't. It would push out in all of them. But again, if you think about, and not that this is necessarily the best analogy to make, but there is a reason why these electrons are in those positions compared to everywhere else. They're not distributed in, well, here they are obviously in a torus. So again, are there similar mechanics that can cause the plasma from this, if this is the pulsar, to push out only in one direction? Who knows? I don't know. With a lot of these things, there are so many different ways to look at it, and so many questions that one question leads to another question, which leads to another question, and then you're kind of back at the first question because you haven't answered the first question and you've gone full circle. But you also said something, the other thing that you said in there was about Platonic shapes, which was, I think, the reason for this one and the reason for these. And this is we're coming back to bubbles. We often look at bubbles and they are spherical, but, in this video, he creates a dodecahedron out of just blowing bubbles. And the beautiful thing is you end up with these very sharp lines along the boundaries of the bubbles. And that for me was another interesting, when you started talking about bubbles, there are, when we looked at some of those, seeing Birkeland currents, there were some of the shapes that did have right angles. And right angles are, difficult to explain if you're just talking about charges flowing in one direction, because, they'll go path of least resistance. Well, what we don't necessarily see is what created the structure that forces them to follow that path of least resistance. And I think this is another demonstration of the fact that spherical things can create straight and angled lines. And again, the question is, when we look at stars, we view a star as just the spherical thing. But obviously, if you look at where's the picture of Betelgeuse, there's much more going on. There's much bigger, like I said, it's bubbles within bubbles, within different types of fluids or different types of medium that they're in. And then you have these boundaries. So the question is, how do some of these structures interface with each other when they come close enough? Most of the stars I'm guessing that we see are spherical because they're sort of sat by themselves. But what would happen if that didn't happen? If for some reason those spheres could touch, what would happen then? What would happen to two? And this is one of the things I do, when you talk about in the EU about the sun being captured, the Saturn being captured by the sun, is what the hell would happen to the double layer, the heliopauls of one of those as it got sucked into the other? Because you can see in some of those shots that you sent of the bubbles, you can stick your hand inside of a bubble and it doesn't burst. There are certain things you can do that keep the bubble intact, and then there are other things you can do that causes the whole bubble to just shatter almost instantly.
Right, and then there was the image of the almost like a front spreading across the surface of the bubble.
Yes, like that was in some sort of a Star Trek film where they're blowing up the planet, and it's sort of in a triggered event. There's a very slow, it's obviously in slow motion, but there's an effect there that it travels across the surface. It's not instantaneous. So again, 3 different scenarios, but they're all the same bubble. One, it's unaffected. One, it instantly collapses, and another one where it's sort of slowly exploding from one side to the other. And again, does that happen? When we look at the plasma in around stars, what happens with those?
Yes, we do see like waves of like. I mean, if you just stick with the mainstream theory for now, just because a lot of their observations are in those terms. Like when they see expanding shock fronts moving away from stars, they'll sometimes see, recombination. That a shock front it's a double layer, like the electrons are driven out in front of the ions. But as it expands and slows, you get recombination, and that's really a collapse of those double layers, if you want. And that has to happen too at bubbles if there are double layers. Then you can just imagine the difference in those experiments where they put a projectile, which obviously is going to be charged relative to at least one of the double layers, if not compared to the whole object, and then compared to touching it when you can keep providing whatever current it needs. That's different than a charged object hitting it, and you can almost see the difference in the dynamic that way too.
There's a lot that bubbles can teach us, but it's about how to sort of unlock that in terms of understanding. And for me, I guess there are a number of points that I think are worthy of it being something that is necessary for us to look at. And one is this idea of the fact that when it approaches, another double layer, that there is this sort of process whereby the far end keeps going and initiates the collapse, and you end up with this beam. So the formation of these jets that are directed towards it. That sonoluminescence, I think, is another interesting aspect. I'm not saying that necessarily is why the sun is powered, but is that a spark that triggers some sort of event? And certainly the fact that we... Go on, Jim.
Right, like that. Well, I was going to say, like the how the sun, that's not quite the same as far as like the flash of light you get with a supernova isn't intense, where a star that might not even be obvious in the night sky might suddenly be the brightest thing out there, all in just that flash. So that's quite a bit different than that collapse of that stellar bubble is more like the event we get with the collapse of a bubble, rather than the reason the sun in general shines. It has nothing to do with that. Not at that scale. It's at any rate.
Yes. Yes, I'm still thinking about the initiation, what causes that initial process to start. So I'm back more at the beginning of the formation of the whole thing. So how do you start the seed event that creates the imperfection that causes the first bubble to form, that then forms the star inside of it? And then, as you say, the whole concept of what we see is the flash, the supernova. Is it that collapse? But then the question for me is, which bubble are we talking about? Because effectively there are two bubbles. There's the bubble that is the sun or the star, and there is the bubble that is the heliopause around it. Do they both collapse at the same time, or does one collapse and shatter the other one from the inside, or does the outer one remain intact? Do they account for different variants of the same thing? Brighter, bigger ones, more energy from a larger collapse? And I think also in terms of the bubbles, the fact that when we look at supernovas that you end up with a material being ejected outwards. Again, if we're talking about a positively charged star within this bubble, then obviously if you break that double layer, there's nothing to hold that matter inwards. And if they're all positively charged, either they will start flying off in all directions. Which is what we see in terms of an explosion. Is that explosion not because boom, but more because of the charges and the fact that double layer has suddenly collapsed? Not collapsed, but disappeared. So it's more the effect of the double layer disappears, and that causes the material to go outwards. Or is it that you get cavitation, so the bubble collapses, and then you end up with the sort of the as it shrinks in the material then gets thrown outwards, and you end up with the flash.
Yeah, that double layer is the most interesting thing.
I hope you enjoyed this initial investigation into bubbles. I will be looking at further aspects of this in the near future. If you have any thoughts on this, then please don't forget to leave a comment and hit that like button. As always, be brave, be curious, the truth is waiting for us. Until next time.